In this tutorial, we will be discussing the properties of matter. Properties of matter are observable, measurable characteristics. They're used to describe, classify, and identify substances, and can be expressed as either qualitative or quantitative. For instance, the physical state of matter is considered a qualitative property. We can break this down into solids, liquids, and gases. A solid holds its shape and has a very fixed volume. A liquid, however, takes the shape of the container but still has a fixed volume. And a gas takes the shape of the container and the volume of the container. The molecules spread out. Let's look at solids a little bit closer. You can then break solids down into either crystalline solids or amorphous solids. Crystalline solids are atoms or molecules that are arranged in repeating patterns, whereas amorphous solids are atoms or molecules that have no long-range order. So, for instance, quartz here is very structured, whereas the amorphous of glass, the shape of glass, isn't so structured. It's a little bit more random. Let's look at qualitative and quantitative a little bit closer. Qualitative is an estimation. You don't need any measuring device to do this. It could be dependent on color. It could be talking about the odor. Quantitative, however, is a value in the appropriate units, such as length or perhaps weight. You need to use a measuring device or an instrument to perform these properties. So quantitative properties are reliable measurements that need proper selection of the use of measurement device. What this means is, for instance, volume. Use a graduated cylinder. You never, ever, ever use a beaker for volume. Even though there's volume gradients there, they're not very accurate. So the more accurate your device is, the better the results will be. And the appropriate set of units, for instance, metrics or SI units. You could also use scientific notation, which is the ability to compactly express large or small numbers. And dimensional analysis can be used as well to convert units as necessary. This is also called factor label or unit factor process. Properties can be broken down to intensive or extensive properties. Intensive properties do not depend on size or the extent or the amount. Those all mean the same thing. So in other words, if I have a glass of Kool-Aid, it doesn't matter if that Kool-Aid is 1 ounce or if we have an entire glass of Kool-Aid. It's still going to be red. They only depend on the identity, the purity, and the conditions of the measurement, such as temperature and pressure. They are not additive. Extensive properties, however, do depend on the amount. So this is things like weight or length. They are additive, and the different materials can't have the same value. For instance, we could have 1 gram of feathers and 1 gram of bricks. It's still going to be the same value even though they're two different substances. Properties are either intensive or extensive. They're never both. So let's go through some examples. Color would be considered an intensive property because it doesn't matter how much you have. Odor, again, is considered intensive. Mass depends on the amount, so the more you have, the more it's going to weigh. That's going to be extensive. Once again with weight, the more you have, the more it's going to weigh, so it's going to be extensive. Malleable is a fancy word of saying it's bendable. You can shape it. Because it doesn't matter how much you have and it's still shapeable, it's going to be intensive. Volume, the more you have, the bigger the volume is going to be. That's going to be extensive. Melting and freezing points, it doesn't matter how much you have, the melting points will still be the same. Density, once again, it doesn't matter how much you have. If you have a few grams of a piece of wood or an entire log, it's still going to have the same density. Hardness, once again, it doesn't matter how much you have. Length, it does matter, so it's going to be extensive. And finally, conductivity, it doesn't matter how much you have, so it's going to be intensive. Matter can be broken down into two different categories. One is pure substances. These are substances that are made of single type of an atom or a molecule. It can then be broken down into elements and compounds. Elements are a substance that cannot be broken down into any simpler substances, whereas a compound can be broken down, but it has to be done through chemical means. So it's composed of two or more substances that are chemically bonded together. Mixtures are the other category. These are two or more pure substances that are combined, not chemically. So that can then be broken down into homogeneous and heterogeneous mixtures. Homogeneous, or you might hear it called homogeneous, are two or more substances mixed with the same composition. Or it could also be called a solution. So things to think about is, does it look like the same no matter where you look at it in the jar? Does it settle out? If it settles out, it's not homogeneous, it's not homogeneous. It has to stay in solution. An example could possibly be Kool-Aid once again. The first drink of Kool-Aid and the last drink of Kool-Aid should taste the same. Iced tea is the same way. Heterogeneous, however, are two or more pure substances with varied composition, meaning it's not going to be exactly identical everywhere you look at it. Think of maybe the beach. Every grain of sand in the composition of every area on the beach is not going to be exactly the same. Therefore, the beach is considered a heterogeneous mixture of the sand. It does settle out over time. So let's say, for instance, you took the Kool-Aid and you put too much sugar in it, and the sugar dropped to the bottom. Well, then it's no longer considered a homogeneous mixture. It's now heterogeneous because the sugar is on the bottom. And these could also be called colloids or suspensions, because of the fact that you can see the particles in the jar. So just to give you a flow chart, so that way you can visualize what's going on here. If we're trying to classify a piece of matter, the first thing you want to ask yourself is it a mixture or is it a pure substance? If it's a mixture, that means you can separate the pieces out physically by boiling or something along those lines. You can then break mixtures down into heterogeneous and homogeneous. Heterogeneous means that they are not mixed evenly, or they'll settle out. They don't look the same everywhere you look at it, or they'll settle down to the bottom if you let it sit there. Homogeneous is also called solutions, and they do look exactly the same no matter where you're going to look at it. They also do not settle out over time. If you look over here at substances, these are pure. They're either elements or compounds. The elements are single atoms. The compounds can be broken down into the elements, but you have to separate them chemically. You have to do a chemical reaction in order to make it break down. So let's take some practice with this. Jello. No matter where you look at the Jello, it should look all the same. However, it is a mixture because you have the water combined with the powder stuff. So it's considered a homogeneous mixture. Mint chocolate chip ice cream. The chocolate chips are in the ice cream sporadically, so therefore it's going to be heterogeneous. It's a mixture, but it's not mixed evenly. Chicken noodle soup, same kind of ordeal. It's a mixture and it's not mixed evenly. It does not look the same every place you look at it. So it's hetero. Helium is right off the periodic table. It's an element. Water is not on the periodic table, but it is a pure compound. It's H2O. So therefore, it's a compound. A diamond. That's a trick question, actually. A diamond is pure carbon. Since carbon is on the periodic table, that means it's an element. Tea is considered to be homogeneous because your first sip of tea and your last sip of tea should taste the same. Iced tea, however, when we add ice to it, the ice floats to the top. So that means the top of the tea will probably be more dilute than the bottom, making it then heterogeneous because it's not the same all the way about. Sour cream. Sour cream and peanut butter are both trick questions. When you open up the jar, it looks like it's mixed evenly. However, if you let the sour cream sit for a while, water will rise to the top, meaning it's separating it out. Since it's separating it out, it's considered heterogeneous. Peanut butter will do the same thing. If you let it sit there, the oil will rise to the top, making it heterogeneous. Sodium chloride is sodium and chlorine bonded together, and that's a compound. You have to have a chemical reaction to separate those. Same with carbon dioxide. And finally, oxygen you will find on the periodic table, meaning that it's an element. And those are some reviews of the classification of the matter. Let's look at the physical and chemical changes. As we said before when we were looking at this chart, we can separate mixtures physically to form substances, and we can separate compounds chemically to form elements. So let's take a look at these physical and chemical changes. A physical change will affect its physical property, while a chemical change will affect its chemical property. The physical change will alter the state or the appearance. For instance, if you melt ice, now it's a liquid, but it's still considered H2O. Where with a chemical change, the atoms are actually rearranging themselves into a totally different substance. A physical change is an extensive property, meaning it matters the amount, whereas a chemical change is an intensive property, meaning that it's going to alter something like its density or the way it's going to react. With physical changes, you can change back very easily by, for instance, the water we were talking about. If we put it back in the freezer, we can easily put it back together into a solid. Whereas with chemical changes, you need a chemical reaction to change it back. The bottom line is, when you're trying to decide between a physical change and a chemical change, you have to ask yourself, is it still considered the same thing when you're done? And can you easily undo it? If it's considered the same thing afterwards, for instance, if you rip a piece of paper, it's still considered paper, just smaller pieces. Therefore, that's a physical change. However, if you take that piece of paper and you set it on fire, then suddenly you're creating ash. Well, that's no longer considered paper, so therefore that's a chemical change. So you have to ask, can you change it back easily, or is it still considered the same thing afterwards? So let's do some practice. Butter melting. Well, if we cool the butter back down, it will turn back into a solid. So butter melting is turning it from a solid to a liquid. Well, we can turn it back into a liquid easily, so that's going to be physical. Wood rotting. Once the wood rots, you can turn it back into the piece of wood again. So therefore, that's chemical. Melting gold. You can cool it down again very easily, making that a physical change. Grating cheese. Well, we can't really put the cheese back together unless we melt it and cool it. But the fact that it's still considered cheese after it's grated is an easy way of thinking that it's a physical change. Turning sugar to caramel. By doing this, you have to put it on the stove and warm it up. And you'll notice that the sugar actually changes color. And there's no way for you to get it back to sugar again unless you do a chemical change. So therefore that's a chemical reaction. A nail rusting. Once again, you can't unrust a nail. You can take the rust off, but that rust that fell off is still rust. So therefore it's chemical. Digesting food. You can't undigest food. Therefore it's chemical. Lighting a stove. Once that gas burns, you can't unburn it. Therefore, that's a chemical. And tearing a piece of paper, we talked about this earlier, you still have paper when you're done, therefore that's physical. And those are some overviews in practice with physical and chemical changes.